Okay, here we go. Well, if you're like me, you've often wondered what happened to the Jetsons' future that we were so excited about growing up. We have watched as electronics have advanced year after year, decade after decade, while at the same time observing virtual stagnation in the realm of physics. Why, after a century, is there still no grand unification of physics? Why, nearly 6 decades for 6 decades, has the vacuum catastrophe of the cosmological constant problem persisted? You see, QED, quantum electrodynamics, predicts a vacuum energy density 120 orders of magnitude higher than what is observed, which, if true, would mean that we wouldn't be here. Despite QED being the poster child of modern physics, it also holds the biggest blunders in physics history as well. How many more decades or centuries must go by before we start to ask, is there more to physics? Before we can understand where we are, we must understand where we have been and how we got here, because context is important. Well, it all started with blackbody radiation. The period from the 1860s to the turn of the 19th century saw rapid advancements in thermodynamics, electromagnetism, and optics, with blackbody radiation emerging as a stubborn puzzle that exposed the limits of classical physics. Our story begins in 1860, when Gustav Kirchhoff introduced the concept of the blackbody as an idealized perfect absorber and emitter of radiation, and became a key area of study in the late 19th century, when classical physics failed to explain its spectrum. By 1890, it was a hot topic in academic circles. Then, in 1900, Max Planck published his groundbreaking formula for the black body spectrum in his paper entitled On the Law of Distribution of Energy in the Normal Spectrum. It explained the observed energy distribution was assuming that energy that is exchanged is in discrete packets, or quanta. If you were a physicist during this time period, the buzz after Planck presented his paper to the German Physical Society felt urgent and existential. Despite how well Planck's paper and formula were received, he himself was not satisfied with the presence of Planck's constant in his formula, as it was a purely mathematical assumption. Dissatisfied, he continued his analysis for a decade, when in 1911, he published his second paper entitled, quote, A New Radiation Hypothesis, where he again derived the blackbody spectral formula, but this time with an excellent reason for the presence of Planck's constant. His new equations pointed directly to the existence of a very real energy source, what would become known as the zero-point energy. What happens next is frustrating. Over the next decade, prominent physicists such as Walter Nernst, Otto Stern, and Albert Einstein gave credence to its real existence. Even evidence and proof of a real ZPE came from chemist Robert Mulliken in 1925, and later Willis Lamb and Robert Rutherford in 1947. Today, the Lamb shift of spectral lines is quoted as an observational proof of the ZPE. However, despite Planck himself producing a new paper and support from leading scientists as well as eventual evidence and proof, the scientific community had already taken his first paper and run with it. In the 1920s, 4 papers were published in 4 consecutive years, all of which used mathematical explorations of Planck's first theory devoid of a real zero-point energy. These 4 papers were, in summary, Louis de Broglie in 1924 proposed that just as experiments indicate that light waves could sometimes behave as particles or photons, depending on the measurement, so a particle under some circumstances might also behave as a wave. Paper number 2 was in 1925. Max Born, Werner Heisenberg, and Ernst Pascual Jordan developed the initial form of QED quantum mechanics, with Paul Dirac formulating his own version as well. In 1926, Erwin Schrödinger, after musing over the significance of de Broglie's proposal for 2 years, proposed the wave mechanical theory of the hydrogen atom, from which the Schrödinger equation originated. Finally, in 1927, Heisenberg published his uncertainty principle. Despite Planck's second paper in 1911 postulating a real ZPE, these four papers turned the course of physics away from the classical approach and toward what is known as quantum electrodynamics. This approach treats the ZPE as hypothetical and only useful as a mathematical construct. Decades go by, and in 1962, Louis de Broglie, a physicist who had written one of those four papers, changed his mind. He published a new book entitled New Perspectives in Physics, in which he suggested that physics may have taken a wrong turn in the 1920s. His paper initiated a re-examination of Planck's second theory. This examination concluded that the quantum processes written about in the four papers that had swung physics toward QED in the 1920s had viable explanations in classical physics if it assumed that the zero-point energy field is real. In 1966, Edward Nelson published a paper furthering the sentiment. From the abstract, he stated, "We shall attempt to show in this paper that the radical departure from classical physics produced by the introduction of quantum mechanics 40 years ago was unnecessary. An entirely classical derivation and interpretation of the Schrödinger equation will be given, following a line of thought which is a natural development of reasoning used in statistical mechanics and in theory of Brownian motion." Now, this was an indirect reference to the ZPE. From there, a steady stream of papers was published through the 1970s using the ZPE approach. This approach came to be called Stochastic Electrodynamics, or SED. The name comes from the random or stochastic distribution of the ZPE waves in the vacuum. Stochastic Electrodynamics. SED is a semi-classical scientific framework that treats the zero-point energy field as real. In essence, it is the fundamental science of the ZPE. With a real intrinsic ZPE and a purely classical interpretation, SED physics has been able to derive and explain blackbody radiation and Heisenberg's uncertainty principle and the Schrödinger equation and the wave nature of subatomic matter, all factors that interpreted without the ZPE gave rise to QED concepts in the 1920s. Starting with Louis de Broglie in 1962, and then a steady stream of papers published through the 1970s using the ZPE approach, SED started to gain traction. It was a very slow progression without much buzz, that is, until the mid-1980s, when an American physicist would storm the scene, framing the quantum vacuum as an inexhaustible energy source. His name, Harold Edward Puthoff. Hal Puthoff, as he is called, is an American electrical engineer and parapsychologist known for his work in laser physics, remote viewing research, and theories on zero-point energy. Puthoff's contributions revitalized SED as a classical framework with real electromagnetic zero-point fluctuations. In his 1987 paper entitled Ground State of Hydrogen as a Zero-Point Fluctuation Determined State, he modeled atomic stability via ZPF-driven orbits, where electrons absorb and radiate energy in balance per Lorentz forces. His 1989 paper, Gravity as a Zero-Point Fluctuation Force, hypothesized gravitation from ZPF pressure imbalances, a concept built on Andrei Sakharov's proposal in 1968 that the gravitational constant was a consequence of zero-point fluctuations in the vacuum. With Bernard Heisch and Alfonso Ruda, Puthoff's seminal 1994 paper, Inertia as a Zero-Point Field Lorentz Force, posited mass as emergent from ZPF resistance. With these papers as a foundation, Hal Puthoff generated an urgent and existential excitement similar to that of Max Planck's first paper in 1900, and invigorated not just scientists, but the military, investors, foreign nations, and the public by framing the quantum vacuum as an inexhaustible energy source. He envisioned revolutionary applications, from washers, dryers, and heaters being unplugged and powered by compact ZPE units, to future aircraft carriers sailing eternally on ZPE drives. Investors jumped on board. Government grants and contracts became abundant. He claimed talks and proposals with Arab oil producers to invest ZPE in ZPE to offset petroleum losses with the advent of free energy. That's a lot of buzz to look around now in 2025 and not see any ZPE powered homes. So what happened? Are we to assume that none of it worked out? Not necessarily. Anyone with an authority on the subject will not talk about it, because anyone with that kind of knowledge is bound by NDAs, especially Puthoff. That in and of itself is telling. Are we to assume that Puthoff's papers were the complete science on the matter and that there's nothing more to be learned? Absolutely not. And so we have a purpose to learn more and to press on. Let's recap Puthoff's version of SED. The version that we know about is a Lorentz invariant classical theory treating the ZPF as tangible waves, sustaining quanta, inertia, and gravity, sans QED's renormalization hacks. See, QED uses mathematical tricks to subtract infinities from equations, normalizing divergent vacuum energies without physical basis. Example, the cosmological constant problem. He advanced experiments like Casimir force validations and ZPE extraction concepts, pushing vacuum engineering frontiers. The problem? Puthoff assumes a static ZPE density, constant across cosmic time, and with fixed physical constants. This limits it to local phenomena, ignoring redshift anomalies and QED's cosmological mismatches. This doesn't mean Puthoff didn't realize this and continue to follow the science. But with his and others' NDAs, it just means it's incumbent upon a new generation to pick up where those NDAs probably left off. Enter Barry Setterfield. Barry Setterfield is an Australian physicist and researcher known for many works, including cosmology and the zero-point energy. Setterfield, building on Puthoff's atomic orbit sustenance and inertia as ZPF Lorentz forces, hypothesizes boldly with an expanded view of SED, everything from the speed of light to Planck's constant to elementary charges to gravity, mass, and inertia, and by nexus, the laws of thermodynamics are all emergent properties of varying ZPE density. This fixes QED's blunders, explains observed cosmological quantized redshifts via ZPE mode interactions, and posits a static universe where ZPE loans order for emergent constants and thermodynamics. Under Setterfield's expanded SED, all physical constants emerge from zero-point energy density. In other words, from the vacuum's thickness. Effects of or on constants with ZPE changes. Setterfield's data, from redshift anomalies to atomic clocks and plasma cosmology, shows that constants aren't fixed, but ZPE derived. And not only ZPE derived, but with the assumption that the ZPE has and does change density, cosmologically over time and locally now. Imagine a box, like an AV receiver, with a big volume knob. Turning the knob clockwise increases ZPE density in the local vicinity. Now, as ZPE density increases, you'll have things happen like the speed of light decrease or Planck's constant increase, just as a couple of examples. So you should now have a basic but comprehensive grasp of the history of the ZPE, from its initial discovery by Max Planck to its dismissal as a mathematical construct under QED, to its revitalization as a real electromagnetic field under the science of SED, starting in the 1960s through the 1990s, a little bit of a quiet period from the early 2000s until today. With the advent of AI and plasma fusion technologies, ZPE is buzzing once again. Now with Setterfield's expanded emergent constants and varying ZPE density in mind, let's take a focused look at what the ZPE is. Whereas standard QED physics considers the ZPE to be a purely mathematical construct, SED considers it to be an inherent electromagnetic field of all wavelengths moving in every direction. Even if you were to perfectly seal a vacuum and cool it to absolute zero temperature so that all thermal radiation has been removed, there would still be measurable energy inside. For this reason, it is called zero-point energy. We don't notice it for the same reason we don't notice atmospheric pressure on our bodies. It is the same within us as it is outside of us and our measuring devices. The ZPE was discovered to be all-pervasive across the cosmos. The zero-point energy controls the mass of subatomic particles. Subatomic particles are usually assumed to be charged, without mass and in need of a mechanism to impart mass to them. QED's answer to this was the Higgs boson. However, there are lingering scientific doubts as to whether it does what the theoretical model wants it to do. In SED, the random battering of the ZPE waves impart motion to the point charges of the various subatomic particles. It is this kinetic energy that gives subatomic particles their mass. The ZPE sustains electrons' orbits. An electron orbiting a proton radiates energy. At some point, it should spiral into the nucleus. But that doesn't happen. QED invokes quantum laws to explain this, but SED has a simple solution. The ZPE sustains their orbits. In 1987, Hal Puthoff wrote, quote, "Finally, it is seen that a well-defined, precise, quantitative argument can be made that the ground state of the hydrogen atom is defined by a dynamic equilibrium in which the collapse of the state is prevented by the presence of the zero-point field fluctuations of the electromagnetic field. This carries with it the attendant implication that the stability of matter itself is largely mediated by ZPF phenomenon in the manner described here, a concept that transcends the usual interpretation of the role and significance of the zero-point fluctuations of the vacuum's electromagnetic field." End quote. Thus, under SED, the very existence of atomic structures depends on the ZPE to sustain them. In other words, without the ZPE, all matter in the cosmos would collapse. Articles in New Scientist discussed this in July of 1987 and July of 1990 under the heading, "Why Atoms Don't Collapse." Well, how much energy is it? Physicist Richard Feynman and others have posited that the amount of ZPE in 1 cubic centimeter of the vacuum is upwards of 10 to the 37th joules. To put that into perspective, if we take the roughly 200 billion stars in our galaxy and assume their average radiation intensity is the same as our sun, and they all shine for 10 billion years, that is less than the ZPE energy found in 1 cubic centimeter of space. Now, I'm not German, and so forgive my pronunciation. Zitterbewegung. The ZPE consists of many more short wavelengths than long ones. For this reason, the vacuum is smooth and featureless at the scale of meters and centimeters, and yet a seething sea at the scale of molecules and atoms. Because the ZPE consists of far more short wavelengths than long wavelengths, most of the effects of the ZPE occur at the atomic level or smaller, where vast numbers of waves at short wavelengths travel in all directions, each with their own electromagnetic field. These all-pervasive zero-point fields are homogeneous and isotropic throughout the cosmos. This is true all the way down to what is known as the Planck cutoff length, where the smallest wavelengths are absorbed into the fabric of space. This means enormous turbulence on the atomic scale. Atoms and subatomic particles get jiggled by the impacting waves of the ZPE, giving rise to quantum uncertainty in their position and momentum, jiggled being the German word zitterbewegung. According to SED, the electron undergoes about 10 to the 20th random hits per second. This is also known as the Compton frequency. Impacting waves cause an electron to jitter and change directions 18,700 times per orbit around the atomic nucleus. Some ZPE effects that you may not be aware that you're aware of. This jittering of subatomic particles by the ZPE explains why cooling alone will never freeze liquid helium. Unless pressure is applied, ZPE fluctuations prevent helium's atoms from getting close enough to solidify. In electric circuits, ZPE fluctuations cause a random noise that places limits on the level to which signals can be amplified. This noise can never be removed, no matter how perfect the technology. Virtual particle pairs. Because the electromagnetic waves of the ZPE are of all wavelengths and traveling in all directions at once with random distribution, they are akin to waves of the ocean. They will inevitably meet, and as ocean waves crest and form whitecaps, so too the waves of ZPE constructively interfere to form a concentration of energy in the form of particle and antiparticle pairs. Because these particle-antiparticle pairs will almost immediately recombine and go back into the ZPEC, they're known as virtual particles. However, unlike in QED, these virtual particles, for their very short existence, are very real and can and do absorb light. This occurs because energy and mass are interconvertible. They appear as particle-antiparticle pairs in order to maintain conservation of electronic charge. There are many kinds of particle pairs, including electron-positron pairs, proton-antiproton pairs, and positive and negative pions. In any instant, there are over 10 to the 63rd such particle pairs in any cubic meter of space. To put that into perspective, the observable universe only harbors 10 to the 23rd to 10 to 24th stars in total. So double the amount of stars in the known universe, and you are still not at the number of virtual particle pairs in any given cubic meter of space. Setterfield's expanded SED. If the strength of the ZPE increases, then the number of virtual particle pairs present at any given moment also increases in proportion, and vice versa. Because the virtual particle pairs are electrically charged, they control the electric properties of the vacuum. Of course, these charged particles also move, and a charge in motion produces a circling magnetic field. For this reason, the VPPs also control the magnetic properties of the vacuum. The extent to which the vacuum permits itself to be polarized in an electric field is called the permittivity of free space, denoted by the Greek letter epsilon. The degree to which a magnetic field can permeate a substance is called its magnetic permeability, denoted by the Greek letter mu. If ZPE density increases, then both permittivity and permeability of the vacuum also increase proportionally. In other words, the vacuum is polarizable. Any change to ZPE density will affect both permittivity and permeability of the vacuum. In contrast, under QED, the number of virtual particles is solely dependent on the Heisenberg uncertainty principle and used only as a mathematical construct. What is possible under SED? As stated before, SED is the science of the zero-point energy field. Given everything that we have covered today, it is time to ask the exciting question, what is possible with stochastic electrodynamics? I envision a future very soon with stochastic electrodynamics mobilized by quantum vacuum propulsion. Imagine your Amazon packages being dropped off by propeller-less drones. No loud noises, no rotor wash. Imagine people moving in and around towns and cities in air taxis, quietly and without that annoying rotor wash. Imagine spacecraft being able to go up into orbit and hover there at 0 miles an hour without the need for millions of pounds of rocket fuel, without the need for escape velocity without the need to travel 17,000 miles per hour once you run out of fuel just to keep from falling back down to Earth. This is the future that I see with Barry Setterfield's expanded SED and a very real ZPE. I first became fascinated by the zero-point energy field in August of 1998. At that age, I could read everything I got my hands on in terms of quantum mechanics, special relativity, general relativity, gravity. I mean, I really wanted that Jetsons future. And then I came across this exact copy of Discover magazine, August 1998. You can still see highlights in this article that feature Bernard Heisch talking about the zero-point energy field in terms of faster than light travel. It was a very fascinating article. Imagine my disappointment more than 20 years later and we still don't have faster than light travel. But faster than light travel in ZPE is not what carried all the buzz. As we learned earlier, how Puthoff created buzz around the ZPE being an infinite energy source and the buzz around tapping into the ZPE for free energy. Now, one quick swig of water. And here is what I have to say about that. I am not a proponent of free energy. There's no free lunch and there are no perpetual motion machines. Let's say you have a paddle wheel that you stick under a waterfall. You attach a rod to the wheel and gears to the rod. You can do work. But that is not free energy. You have efficiently engineered and designed a system. You've engineered the system of energy that's present to efficiently loan order in one place that is repaid entropically somewhere else. And that is what I call foundational cornerstone number one, no free energy. The system, you can design it to loan order one place that is repaid entropically somewhere else. Analogy number two, the ocean. The ocean is vast. The ocean is powerful for all intents and purposes. It is an infinite energy source. And yet, we don't stand at the edge of the ocean and say, how can we tap into this seemingly infinite energy source for free energy? Well, people probably have, but there's a very simple reason why we don't. They figured out it's not a very efficient use of the system. Well, what do people use the ocean for? Navigation. They figured out you could build ships that use propellers that push off against the medium of the ocean for thrust, for propulsion. Likewise, my idea is that we can sail the quantum sea in much the same way we sail the ocean. So what did people design? They designed ships with propellers. Well, what does a propeller do? A propeller is designed to create higher pressure on one side of the blade, lower pressure on the other side. That creates a directional force for propulsion. And so when people talk about the ZPE being so much energy and so many virtual particle pairs, it's talked about in terms of density. A density, I believe, can be treated as a medium that we can push off of with something of the effect of nanopropellers. I've had this itch in the back of my mind for years. Can't we design nanopropellers to push off the quantum vacuum for propulsion? Well, is there something at the quantum level that does create higher and lower pressure, a pressure differential? Turns out there is. It's called the Casimir force. The Casimir force is when you have two very tiny, very small plates that are very close together, nanometers apart, and there's more ZPE waves outside of the plates than there are inside. This causes immense pressure pushing the plates together. Well, you're on your way to a propeller right there. And so I got to work early this year in 2025 designing a MEMS array, a micro electrical mechanical systems device using Casimir cavities for the purpose of quantum vacuum propulsion. I worked on this for months, iteration after iteration, simulation after simulation, until I finally ended up with a completed and fabrication ready engineering design package for what I call the ZPF array. I originally had a different name for it, but I'd like to thank John Marsh, the university administrator for Rice University, for graciously giving me his time in in-depth discussions about Rice's shared equipment authority, fabrication, nanofabrication facilities, and the ZPF array. He offered me some wise counsel, which I heeded. So thank you, John Marsh. And also I'd like to thank Mr. Jeremy Ernst from the Embry-Riddle Aeronautical University. He is the Vice President of Research and Doctoral Programs. Thank you for giving me some of your time to talk about possible future projects of getting Rice University in the lead, pioneering quantum vacuum propulsion with maybe something like Rice's Shared Equipment Authority, and looking forward to talking to you more about that. And so after my engineering design package was complete, I went to Bold Patents in Houston and got started with the patent process. They ran the 2-month prior art check, which did come back clean. And then I started 0 Point Field Technologies, LLC, and then transferred the ownership of the ZPF array patent, provisional patent, to the company. So the company now owns that. All that to say this, I won't get into all of the minuscule details of the ZPF array for IP purposes. So the 30,000 foot view is this idea I had: can't we push off the quantum vacuum with nanopropellers? So as we discussed, it's a MEMS array with millions of Casimir cavities on it. Now, obviously, the Casimir cavities cannot be parallel plates because they would just get forced together. So they have to be non-parallel plates. You could call them wedges. And number two is this ZPF array is not designed for energy extraction. It is my belief that it is a lot more efficient to use it for navigation, not extraction. That's foundational cornerstone number 2. And so with that, the Casimir cavities cannot be static. And really, that's all I can say about that. They are non-static Casimir cavities, which also means, number 3, that they have to be powered. And so the ZPF array is powered by a battery with up to 10 watts of power. And when turned on, simulations show a directional thrust of between 0.6 and 2.4 newtons of thrust. So what you could do, you could plug in the ZPF array, which is thumbnail sized, to a battery, put that on a derby car, put the derby car on a track and turn it on, and the derby car would continuously accelerate until friction, resistance slowed it, or the battery was exhausted. And so that is quantum vacuum propulsion. Now, I didn't stop there. I wondered if I could design a propeller to get a bigger bite out of the ZPEC. And so I thought of Barry Setterfield's expanded SED with emergent constants from the ZPE. What if I could locally increase ZPE density? Could I get a bigger bite? Well, so I thought best way to do that is a hydrogen atom. You jitter a hydrogen atom that creates secondary electromagnetic fields, and then more virtual particles, which should increase thrust a tiny bit. And so simulations did in fact show a tiny increase in thrust. That's not the exciting part. The exciting part is what happened next. I said hydrogen. I also incorporated borane. So what I did was I put hydrogen borane gas channels through the substrate of the ZPF array underneath the Casimir cavities. Simulations showed trace amounts of alpha particles appearing in the gas chambers. What the heck are alpha particles? This is where it gets really exciting. This is where we transition to start talking about aneutronic fusion. So first we compare that to what we're more familiar with, which is nuclear power plants. These things are dinosaurs, they're fossils, they're never coming back. They heated up, they boiled water to turn turbines for electricity, and to do it, they had nuclear waste. What people have come up with right now, and my favorite example is Helion. What they are doing with their plasma fusion reactors is exciting. They plan on powering Microsoft's AI data center by 2028. They are working on this right now. It's never been done before. This is brand new. They're learning as they go. Brilliant minds, love what they're doing. And it is aneutronic fusion. Well, what are they working on? They call it a field reversed configuration. What does that mean? That's just a fancy way of saying how they end up with their toroidal-shaped plasmas. Well, what's a toroidal-shaped plasma for the layman? It's a donut. It's a donut-shaped plasma that they fire at each other. Two of them fire at each other. They meet in the middle, very fast, very hot. Why? To create a fusion of their deuterium and helium. When it fuses, it creates what? Alpha particles. That's 2 protons, 2 neutrons, a helium-4 basically, that can be harvested with MHD coils at a nearly 95% efficiency rate directly into electricity. That's how they're going to power Microsoft's AI data centers. Now, you have power in, you have power out. Right now in the process, they're probably right about break even, but you need more power out than power in for this thing to work. So that's called a Q factor. Q equals 1 is break even. Q equals 2 would be twice the power out than power in. Q equals 3 would be 3 times the power out than power in, and so on. And so that is aneutronic fusion. That's what they're working on. That's what alpha particles are. And so again, simulation showed trace numbers of alpha particles showed up in the ZPF array gas channels. Well, how did that happen? That is the magic of Setterfield's expanded constants emerge from ZPE version and hypothesis of SED. If you increase ZPE density locally, you are increasing Planck's constant. You are, in essence, softening the Coulomb barrier and increasing quantum tunneling probabilities. This allows the hydrogen and the borane in trace hotspots to fuse to create alpha particles that, sure, could be harvested, but there's not enough of them to harvest in the ZPF array. And so you have aneutronic fusion here, and then you have what I call vacuum catalysis. Okay, the vacuum meaning the ZPE, and catalysis meaning assisted. So it's that idea of engineering the vacuum, the quantum vacuum, to lone order in one place that's repaid entropically somewhere else. That was foundational cornerstone number 1. So it assists in the fusion process. I call it vacuum catalysis. So now you have the two terms, you put them together, and you get vacuum catalyzed aneutronic fusion. This is the future. At first, if you incorporate vacuum catalysis into aneutronic fusion, you will get Q greater than 1. You will be able to power AI data centers. And this is just the beginning. We've never done this before. Once we get good at it and learn more about the process, I foresee Q greater than 2, possibly Q greater than 3. For space travel, we actually need to get to Q greater than 5 so that you wouldn't have to carry additional fuel on board. You would power ZPF arrays with vacuum catalyzed aneutronic fusion reactors. They'd never run out of energy. And so vacuum catalyzed aneutronic fusion, ZPF arrays for quantum vacuum propulsion. That is my rant on that. Let me get back to the slides here and kind of do a quick recap with slides. Quantum vacuum engineering, unlocking the cosmos under SED. SED posits the vacuum as a seething sea of fluctuating 0-point energy where physical constants like the speed of light and Planck's constant emerge from ZPE density. By modulating this C, we can engineer emergent phenomena from propulsion to fusion, borrowing order entropically without violating thermodynamics. Key to this is vacuum catalyzed aneutronic fusion, a process where ZPE fluctuations lower energy barriers for clean nuclear reactions like proton-boron or deuterium-helium-3 in plasma fusion reactors, yielding energy without neutrons. Aneutronic means neutron-free outputs, reducing radiation. Vacuum catalyzed refers to leveraging the quantum vacuum to facilitate reactions at lower temperatures and pressures. Central concepts include quantum tunneling, which is the probabilistic leap of particles through barriers via wave functions, boosted exponentially by reduced Coulomb repulsion. This is known as the Gamow factor, a probability factor for two nuclear particles' chance of overcoming the Coulomb barrier in order to undergo nuclear reactions, like fusion. Screening enhances this. Vacuum polarization creates electron clouds that shield positive charges, easing nucleus approach as observed in stellar plasmas. The ZPF array, quantum vacuum propulsion, anti-gravity effects, and an SED testbed. The ZPF array is not merely a device. It is the first deliberate human attempt to engineer the quantum vacuum as a programmable medium, a nanoscale forge where the fabric of reality itself can be reshaped. In the language of stochastic electrodynamics, it is a coherent resonator array that exploits the zero-point field not as a passive background noise, but as the dynamic substrate from which inertia, gravity, and even the fundamental constants of physics emerge, grounded in the foundational insights of Heisch, Ruda, and Puthoff, who posited inertia as a Lorentz drag force arising from ZPF interactions, and extended by Setterfield's variable constants hypothesis. The ZPF array transforms theoretical speculation into empirical machinery. It is at its core a testbed for unifying quantum mechanics and relativity through vacuum modulation, challenging Einstein's immutable constants and Planck's quantum discretization by treating them as emergent properties of ZPF density. To grasp this, consider the vacuum catastrophe. Quantum electrodynamics predicts an infinite or catastrophically high vacuum energy density. Yet, observation yields much less. SED resolves this by modeling the ZPF as a finite classical stochastic field where only a fraction of the field couples gravitationally via virtual particle pair polarization and inertial drag. Now, we didn't talk a lot about that, but that is one of the key differentials between QED and SED, and the solving of the cosmological constant problem is that only a fraction of the ZPE couples gravitationally under SED. The ZPF array engineers this finite zero-point field locally, using millions of tiny Casimir cavities to induce anisotropy. Each cavity creates directional Lorentz imbalances. Fringing fields penetrate subsurface hydrogen-boron channels, stimulating electron zitterbewegung to amplify ZPF density by 10 to 20%. This isn't passive Casimir attraction, it's active vacuum stress engineering, yielding baseline thrust of 0.6 to 2.4 newtons at 10 watts of power. That's quantum vacuum propulsion. Ultimately, its capabilities transcend propulsion, probing the vacuum's deepest symmetries. If SED holds, and the ZPF array's design assumes that it does, the device could, and we didn't talk about this yet, but generate anti-gravity. By polarizing the virtual particles under external fields, it could modulate gravitational coupling, producing upward forces of 1 to 9 newtons per centimeter squared. This isn't anti-gravity as mass negation, but vacuum gradient engineering. So that's a separate upwards force compared to the quantum vacuum propulsion directional Lorentz force across the chip. Catalyzed aneutronic fusion. In fusion, the Coulomb barrier is the electrostatic repulsion keeping nuclei apart. An increase in ZPE increases permittivity. Epsilon increases with denser fluctuations, effectively lowering the Coulomb barrier by 10 to 20%. HRP zitterbewegung jiggles amplify screening, boosting tunneling probabilities and Planck's constant increasing, broadening uncertainties. And the ZPF array, this catalyzes aneutronic proton-boron alphas at lower energies. Hydrogen flow plus fringing fields ionize gas, enabling nuclear pre-excitation. ZPF-induced nuclear pre-excitation refers to the ZPF array's ability to elevate nuclear systems into a heightened vacuum-modulated state short of full fusion ignition. I didn't talk about that earlier. I could have, referring to Helion's reverse field configuration plasma fusion reactor, but basically they're not worried about ignition. All you got to do is extract the energy from the fusion, the alpha particles. And so they just pulse a lot of toroidal-shaped deuterium helium plasmas at each other. And they're not worried about ignition. So I meant to say that earlier. Under SED assumptions, the array densifies local zero-point energy via fringing fields and hydrogen-induced zitterbewegung softening Coulomb barriers. This pre-excites proton and nuclei, exponentially boosting quantum tunneling probabilities for trace aneutronic events, again, sporadic alphas 10 to 100 an hour. Vacuum catalyzed aneutronic fusion here means ZPE gradients act as a non-thermal catalyst and loans fluctuations to assist reactions, repaid entropically without violating conservation. Relation to ZPE array boosts, trace alphas and heat feedback into the cavities, raising nonlinear enhancement, amplifying thrust via stronger Lorentz imbalances, and amplifying anti-gravity if we're doing those tests as well. ZPE Plasmoid Engines for rocket fuel-free space drives. So I didn't do anything in this presentation on faster than light travel, but if you use ZPF arrays for quantum vacuum propulsion in space, that's what this is about. Plasma aneutronic fusion reactors are the future. Not only will they start with AI data centers, they will eventually power the grid. Take that to the bank. Companies like Helion are working right now to achieve Q greater than 1, which is net energy gain. With this technology applied and the Coulomb barrier lowered, vacuum catalyzed aneutronic fusion simulations project Q rising to 1.2 to 1.5 initially. Now that's a 20 to 50% gain, and then scaling to Q greater than 2 or 3 or beyond with future advancements. With vacuum catalyzed aneutronic fusion as the power source, you could then scale the ZPF array. Remember my prototype, I didn't say the size, it's thumbnail sized. Scale the ZPF array and then make many more and then power them with vacuum catalyzed aneutronic fusion reactors. For now, this is my version of a ZPE drive for space travel. A trip to Mars could potentially be done in weeks, not months. And I mentioned before, in order to not run out of energy to power the reactor, we would need to attain Q greater than 5. This would be achievable with scaling and advancements. Ultimately, I hope that we do learn ways to use changes in ZPE density to create either warp bubbles or a macroscopic quantum tunneling for space travel. That would be the ultimate. But with the amount of energy that can be created by using Setterfield's expanded stochastic electrodynamics with vacuum catalyzed aneutronic fusion, first we'll power the data centers, then we'll power the grid. And with that much electricity on hand, you're talking about a potential for an advanced civilization. You're talking about having things that you see on Star Trek, like replicators, with that amount of electricity at our disposal. In conclusion, we talked about the discovery of the ZPE by Max Planck in 1911, the dismissal of the ZPE as a real inherent property of the vacuum with the birth of quantum electrodynamics in the 1920s, the advent of stochastic electrodynamics and a real ZPE in the 1960s, its progression through today, a brief analysis of what the ZPE is, and finally, what is possible with Setterfield's expanded SED physics. I'll just end by saying this. If Setterfield is correct, and the constants in thermodynamics are in fact emergent properties of the ZPE, and if we can successfully increase and decrease ZPE density locally, then we are in essence modifying those constants toward desired effects to lone order in one place that is repaid entropically somewhere else efficiently. And the applications would range across all fields of science, not just energy, not just aeronautics, not just space. ZPF arrays might be extremely beneficial in the medical field, for example. If vacuum catalysis can help aneutronic fusion reach full ignition, which is self-sustaining fusion like a star, then we would have the amount of electricity needed for an advanced civilization like Star Trek type scale, as I mentioned before. And this concludes my presentation. Thank you for listening.